I'm Ishan Goel. Today's session is around saving visitors with sequential testing. Firstly, I would want to get some logistical issues out of the way. If anyone throughout the webinar has any question, please do let me know in Q&A. I'll constantly be checking it. I will be in the fourth slide of the presentation. I'll be showing a QR code to all of you. I have some quizzes, some online quizzes in the webinar, which will help you participate. Uh, will help you participate in the questions I'm asking. So I request you all to join it with your phone. So if you scan the QR code, you'll be able to join the quiz that will go on alongside the webinar. So let's get started. I don't think if there is any problem in listening or my connection, do let me know in Q&A and I'll address whatever is the issue. So starting now. So today's session is on saving visitors with sequential testing. I am sure you must have all heard about sequential testing in the modern A/B testing space. Today I'll be unpacking everything about sequential testing, why it is needed, how did it come about, what is the problems that it creates. So without wasting time, I'll quickly get started. Great. So a little bit about me. So in the past 4 years, I've been doing product and research at VWO in statistics. And me with my team, I have built the enhanced reporting system and the new stats engine for VWO. I have also been writing and speaking regularly about experimentation and specifically experimentation statistics. I have been teaching a lot of internal team members in VWO around the concepts. Further, I've been talking to a lot of customers. I've been listening to their problems. I've been solving their problems around statistics and experimentation. So that is the source of my understanding on what are the most pressing problems today in A/B testing. Finally, I've been learning and reading through books and through online courses on experimentation. Now I've moved out of VWO and I am planning to share my learnings with the wider community. So thank you all for joining. This is a short summary of of the topics that we will go over today in this webinar. So we'll start by first discussing this problem of peaking when you basically continuously look at test results while the data is being collected. We will discuss why it is a problem and what are the biases that it creates and when does it creates those problems. Then we'll be moving to sequential testing and the larger concept of sequential testing. What is defined as sequential testing? Further, I'll be talking about the different solutions that are available in the market today for sequential testing and what are the pros and cons of those different solutions. Finally, I'll be going over some tips and tricks on how to choose between sequential testing and fixed horizon testing. Then how to check if your platform is properly sequentially valid or not. Finally, some tips on how to run sequential tests. So this is the larger summary of the webinar. If anyone has a question, please drop it. Otherwise, I am moving forward. I request you all to scan this QR code with your phones and join the Mentimeter slides that I have. I basically have some quizzes while that related to the concepts that I'm teaching. So it will help you also to apply whatever you are learning. It will help me also to understand basically if people are understanding what I'm sharing or not. And it will make this webinar all the more fun. So you have two ways to join. One is either you go to mentimeter.com and you put in this code, or you can just simply scan this QR code and you'll be good to go. So yeah, I think it should be fine. I'm giving you guys 2 minutes to join here. Please take your time to scan this QR code. For those who join later, I can drop the Mentimeter link in the chat. I have given the link in the Q&A section. So anyone who joins later or is not able to join through the QR code, please join through the link. It will work the same way. Yes, wonderful. So great. Moving ahead, we'll get started. So the first section of today's webinar is problems with peaking and when to look at A/B test results, essentially. So let's start with fixed horizon testing first. So essentially, when statistical significance and the practice of experimentation was developed, when traditional statistics was developed for randomized control trials, the idea was that you'll first collect the control group and the treatment group. You'll collect all the data, and then after collection of the entire data set, you'll calculate statistics only once. And you'll see if the results are significant, you'll pick treatment. If they are not significant, you'll go with control. So that was the original idea when this t-test was developed, when general traditional statistics was developed. If you look in domains like drug trials, clinical studies, like clinical drug trials in medical science, you'll still see that these guys first collect the data set entirely and then apply the statistics. So they estimate the sample size that will be required beforehand. Then they collect the entire data set. Then they calculate statistics only once. So all guarantees of false positive rates and the defined error rates in the statistical significance framework, they hold true if you calculate statistics just once. So this is essentially how traditional statistics was developed. Today, this is called fixed horizon testing, where you estimate the sample size in advance and calculate the statistical significance only at the end. However, in modern A/B testing, this is too inefficient. So when modern A/B testing took off like 15, 20 years ago, the idea was because it was so easy to calculate statistics on the fly while the data is being collected, people automatically started doing that. So if you look at this sample report, what you see here is that if the test is running, you essentially keep collecting the data and you keep calculating the statistics. As soon as the statistics crosses, so the probability to beat baseline, as soon as it crosses 95%, you declare a winner. So as early as possible, you declare a winner. So this is very efficient because it helps you save visitors. It helps you deploy winners faster. And because the scale of modern A/B testing is much bigger, and with the ease of data collection and statistics calculation, this became the general practice in modern A/B testing. So this is where modern A/B testing stands. However, this creates a problem, and I'll share with you guys the problem this creates. So I ran a simulation to show you these problems, and if you focus here, in these simulations the decision boundary was 95%. That a winner will be declared when a 95% threshold is crossed. These are essentially 1,000 AA tests. So both control and variation had a 10% conversion rate. So because it was a simulation, I could control the actual conversion rate. Then I ran a sequential test over these. And finally, what you see here is that the blue line has no peaking. So the blue line only sees the statistics once after the required data has been collected. So we see that the false positives. So since these are AA tests, you should not have more than 50 winners in these AA tests. The false positive rate is 5%, and there are 1,000 AA tests. So statistics says that you would not get more than 50 cases where you get a winner, which would be the false winner. And now as we see that if for just one peak, for calculating statistics once at the end of the test, you do not cross the false positive limit. So this gray line here shows the desired false positive limit at 0.05. However, these three red lines show you increasing number of peaks. When I say peaks, what I mean to say is that people calculated the statistics early into the test, like in the middle of the test, and then stopped the test if the statistics was above 95%. So this lightest line here has 20 peaks, and this can be seen from these steps. So these steps denote the exact point in time where the peaks were made. So that is where the winners were added. The line above this has 50 peaks, and the line even more above this is 100 peaks. So the idea is that the more you peek into the test, the more the chance of getting a false winner. So this is the fundamental problem with peaking that creates the need for sequential testing. Now I have a question for all of you. If you come to the Mentimeter slide, so I guess why is this not starting? Just a second. Yes, you should be able to see the question right now in the screen. Is that screenshot from what does it mean by probability of beating control, Bayesian approach? Okay, before the question, I would want to take up Nikhil's question. Nikhil, this screenshot is okay. This screenshot is from VWO. I searched on the internet. I have a natural affinity towards VWO because that's where I was working and that's the framework I'm comfortable in. But I am not, this is not a sponsored webinar. None of the companies are paying me to advertise them. So this screenshot just happens to be from VWO. The thing about probability to beat baseline is that, yes, VWO is a Bayesian solution. But as I've been discussing on LinkedIn, it doesn't, as long as an uninformative prior is being used, it does not matter. Bayesian and frequentist perform exactly the same. So we can take up that discussion separately. You can ask me questions. For now, you can just simply consider that p-values win when they go downwards below 0.05. Probability to beat baseline is the same, exactly the same. It's like 1 minus p-value into 100. They win when they cross, they go above 95%. I hope that answers your question, Nikhil. Wonderful. So, yes. Great. So, there is this question I have. When does peaking become an issue? And I would go over the 4 options and I would urge all of you to take a jab at the answer. Peaking becomes an issue when statistics are calculated more than once. Peaking becomes an issue when variation crosses significance threshold in the middle of the test. Peaking becomes an issue when a user intervenes and optionally disables or deploys a variation, or all of the above. So I'm giving you 2 minutes here. For those who have joined late or are not yet on the Mentimeter slide, I would urge them to join through the link that I've given in the Q&A. I am curious for... Great. Interesting. Interesting. I'm giving 30 seconds more before we move on. So please. Anyone else wants to try? Great. So I'll explain the answer. Peaking becomes an issue when the user intervenes and optionally disables or deploys a variation. So this is a very regular doubt that people have with peaking, that how can just calculation of statistics actually ruin the results? Like how can just looking at data actually create a problem? So this is true essentially. Looking at data can, like I can essentially fool the system that the system does not know if I've looked at the data or not. And statistics can be calculated as many times as possible. False winners are not a problem, or like peaking is not a problem unless you intervene and deploy or disable a variation in the middle of the test. So what happens is generally when you're calculating statistics in the middle of the test, if it crosses the threshold, then you choose to deploy a variation early. If you do not choose to do anything, then peaking is not a problem. You can look at statistics as many times as you want, but the moment you act upon it, it becomes a problem. And the argument goes the other way around as well, that if you do not have to act upon it, then there is actually no point calculating statistics in a running test and getting extra information than you need. So, but the thing here is that we need to understand that peaking in itself is not an issue. Peaking is an issue when you optionally stop the test in the middle without letting it run its full course. So the correct answer here is a user intervenes and optionally disables or deploys a variation. So thank you all for participating. I'll move to the next slide. Now, why does it happen? So why is peaking an issue? And I'm here showing you some complicated graphs that were generated by David Robinson in a blog post that he wrote. But these, I think, are amazing to explain the issue of peaking and why it happens. So what the traditional statistics framework guarantees us is that if there is no impact of the variation on the target metric, then at any given time that you calculate the statistics, there would not be more than 5% variations or 5% tests with 5% AA tests who have crossed the 95% significance threshold. So if you look here, what Robinson has done, he ran like a lot of AA tests, and he highlighted all those that in the end were actually like below. In the end, they were below the 95% mark. So the 0.05% mark. So below significance threshold. So these red lines are actually those the AA tests that won in the end. Now, the thing to note about these is that at any given point in time, there might be some tests. Like if you look here, there are some gray lines that actually became significant in the middle of the test, but went back to being non-significant towards the end of the test. So in an AA test, this p-value or significance will fluctuate. It will go up and down. And at any given point in the test, you won't have more than 5% values below the significance threshold. So like in the significance region. But the problem is, if you start optionally stopping all the tests that even once they cross this threshold, then the problem what that becomes is that you have much more cases here that actually cross them once. Now, it's a very nuanced difference. If you look here, these gray lines actually go back to being non-significant after a while. These red lines are only the ones that are non-significant at the end of the test. Whereas in this case, all the gray lines that even would have gone to being non-significant later, because they were stopped, they were not run further, they are considered as winners. And that is why you have much more winners in the test. So peaking, that is why it becomes a problem. If you optionally stop, then you do not know even those variations that would retract, that would go back to being insignificant. So that is why peaking actually leads to this increase in false positive rate. Any questions up till now before we move further? Wonderful. Do I have a question here? No, okay. So now I'm going to talk about the three problems that generally can be related to peaking or that generally come up in A/B tests. So the first is the peaking problem, which is when results are continuously monitored and optionally stopped, false winners increase. The second problem is the multiple comparison problem. So it is a close cousin of the peaking problem. That is why I'm talking about it here. Whenever you are calculating multiple statistics multiple times, the false winners will increase. Now, one case is peaking when you are calculating statistics multiple times throughout the test. But the other case is when you are calculating statistics multiple times with different metrics, different variations, and different, maybe if you're splitting the test into segments, then multiple segments. So anytime that you are making more than one comparison in the test, the false winners will increase. So there is a different solution to solving the multiple comparison problem. But generally, the advice to follow here is that you always focus on one primary metric for the decision. And if you have multiple variations in the test, you apply a solution for multiple comparison as well, which is called one for only correction. I'm not going into detail here in the multiple comparison problem, but it is important to know it is a close cousin of the peaking problem, but it is solved in a different way. Now, type M errors. So whenever due to peaking or due to the multiple comparison problem, you get an early winner in the test, uplifts are likely to be exaggerated. That is why a lot of people tell recently that you should actually give your uplifts a haircut. So if I got a winner very early into the test and it's saying a 20% uplift I should be very skeptical about it. Maybe the uplift is not more than 10 or 15%. So I should reduce my estimates of the uplift. So that is the type M errors. Early winners usually show large errors, large magnitudes of uplifts. So that is why type M stands for type magnitude errors. So these are the three problems associated to peaking and generally A/B testing and getting early winners. Now I have a question for you. What will happen to false negatives in peaking? This is a very interesting question. I'll explain what are false negatives. Okay, Nikhil, I'll answer Nikhil's question before moving on to this question. This slide. Nikhil asks that how do I determine the exaggeration factor? Nikhil, it's just too hard to determine the exaggeration factor because it depends on a lot of other things. It depends on the prior uplifts that you have had on the metrics. So there are different ways to tackle the type M errors. There is no one answer. Usually you should just have a conservative estimate, but it's a different discussion on how to estimate. The general advice is just cut it by 25-30%, but it is not an exact solution. So yeah, now coming to this question that I have for you. This is a very interesting question and highlights a very important thing about peaking. So firstly, let's start by defining what are false negatives. False negatives are cases where there was a true uplift in the test. Like there was an uplift greater than whatever defined MD that you have, and you actually did not detect it as a winner. So the idea is that what will happen to false negatives when you are peeking through the test? So in case that there was a true uplift, what is the chance that you were not able to detect it in the test is the false negative rate. So when you're not able to detect it, they are the false negatives. The question is, if you're continuously peaking in the test results, what will happen to false negatives? So yeah, please take a. Two people currently say that they'll decrease. Two people say that they'll stay the same. Anyone else wants to try? If anyone still has a doubt on false negatives, they are the true winners that are not detected as winners in the test. Okay, we have a 50-50 tie here. No one thinks that false negatives will increase with peaking. That's good. Very, very interesting. Very interesting. Anyone else wants to take a guess, or should I move ahead? So amazing. I think audience has got it right. Anything that increases your false positive rate will likely decrease your false negative rate as well. So it's like you are trying to pass through, say you are trying to pass through something through a separator. So say you are trying to pass through, rice through a, what do you say, like a, we call it like a separator. You want to let the smaller rice fall apart and the bigger rice stay as above, maybe, just taking an example. So anything that makes more smaller rice pass through will also make bigger rice pass through. So What I'm trying to say is that because peaking actually increases the criteria of winners, it also increases the criteria of true winners. So false negatives decrease in practice with peaking. So your power of the test increases, but it is not a good thing. Why? Because the idea of an A/B test is to balance between false positives and false negatives. If I had to increase, like if I had to just decrease all false negatives at the cost of false positives, that's very easy to do. There is nothing special about it. So yes, you have got it right. False negatives decrease with peaking. CM. Okay. CM. Oh, thank you. Yeah, it's a CM. Uh, yeah, great. Very, very generous of Aman and Pranav. So now moving ahead to sequential testing, and I'll be explaining what is sequential testing and how do we really solve for peaking errors. So sequential testing is the practice of continuously monitoring test statistics and optionally stopping as soon as possible. The point is that sequential testing needs to be properly corrected so that the false positive rates do not inflate. And when both the things are possible, that you are able to continuously run the test and take early decisions and not impact your false positive rates, both things combined are sequential testing. If just continuous monitoring without the correction for false positive rates is not sequential testing, it is not a reliable method of testing essentially. So when anyone claims that they have sequential testing, you should always ensure that are they correcting for false positive rates or they are just allowing for early decisions. Allowing for early decisions alone does not solve the problem. So this picture here shows a very popular method of how it works. We'll come to it next. So I'll move to the next slide and I'll discuss three solutions that are currently the popular solutions in the market, or these are actually the solutions that we explored. There are some solutions here and there, but majorly these three give you the larger landscape and the most cutting solutions for peaking. So the first approach is the alpha spending approach. What alpha spending approach says is, so basically alpha is your false positive rate, and it is also coincides with the boundary that you are using. So when you have set the alpha to 0.05, then that is the boundary in frequentist tests, or 95% is the boundary in Bayesian probability to beat baseline type tests. So alpha spending says that this is your budget of false positive rate that you can use in the test, which is 5%. And what alpha spending does is that it distributes the whole budget over the test continuously. Now, what this does is that this creates, so if you look at the picture here, I picked it up from Analytics Toolkit. This picture essentially creates a threshold above that is very conservative in the starting, and then slowly becomes more relaxed as you progress towards the end of the test. Anytime the probability to beat baseline crosses this line, a winner is declared. Similar on the other side, which is the futility boundary, which is where you are able to disable the decision. So both boundaries are more conservative. Just a second. I'm showing the right screen, right? Yes. So both boundaries are more conservative in the starting. They become less conservative towards the end. So this is the alpha spending approach. The second is the always valid p-values approach. So famously, this approach was developed by Optimizely back in 2013 and 2014, around that time, I guess. And what they did was they calculated an entirely new way to calculate p-values. So they created a new formula entirely. And this is quite a complicated formula. So the drawback of this approach, one of the biggest drawback was that it was very hard to interpret. So you can implement this formula very straightforwardly and it does control your false positive rates. But as we'll see, this has some drawbacks. They called it always valid p-values or always valid inference. This method is being used by some companies, in my understanding, but mostly this method has gotten less popular now. And alpha spending approach has gotten more popular with time. It is also called grouped sequential tests in some cases. Finally, there is this third approach that we developed at VW. So me and my team, we developed this approach at VW, and we have deployed this, which is that if I show this video to you here, and again, I am highlighting, just a second. So what we do is in this approach is that we broaden out the confidence intervals and hence reduce the significance values based on how far you are from the maximum sample size. So what this does is that it infuses the uncertainty. So in Bayesian statistics, the confidence intervals generally represent the uncertainty in the estimate. So what we understood and what we realized was that basically sequential. So with continuous monitoring, you are more unsure about test results. So the best way to integrate those is directly into the confidence intervals. If we can widen the confidence intervals in the exact proportion needed, then we realized it would be the best way. So it is easier to interpret rather than changing decision boundary. In theory, this approach was derived out of alpha spending, and as we'll see ahead, it performs very similar to alpha spending as well for that reason. Any questions up till now? Okay, great. No questions. Do I have any quizzes? Just a second. Okay, I have. We'll come to that quiz later. Just a second. Great. So now I would want to show you some simulation results for all the three approaches to show you that they work. So these are simulations that I've run myself. And essentially, these simulations, first, they show the false positive rate. So the red line shows the unadjusted values. And I have peaked as many times as possible in this. So like I'm peaking at every 10 visitors, sort of. So essentially, here the red line shows the unadjusted false positive rate, which almost goes above 30-35%. The yellow line here shows always valid p-values. So what we see with our always valid p-values is that they are very good at curtailing the false positive rate. And whatever false positives actually are to be discovered, they are discovered early into the test, and then the approach is mostly stable. Then there is alpha spending and this adjusted confidence. So I also call it the information fraction approach. So since alpha spending and the adjusted confidence interval approach, they are derived from the same method, they perform almost the same. They perform very similar. So the blue line and the green line, they also control the false positive rate as desired. False positive rates are chance of getting a winner when there is no actual impact. So the uplift here is 0%. The maximum sample size has been derived out of 5% MD. Finally, I want to show you the statistical power that comes from all the three approaches. And it is important because only controlling for false positive rate does not solve the problem. We need to balance out between the two approaches. So in this case, the required statistical power is 80%. So using a sample size calculator, we have derived that at these many visitors, we'll have an 80% statistical power with a 5% MD and an actual uplift of 5%. What we see here is that the alpha spending and the information fraction approach, so the adjusted confidence interval approach, both of them perform almost. They have a slight cost in statistical power, but that's very minor. They perform almost similar, even with as many peaks as it gets. Finally, always valid p-values, and this is a larger reason why these always valid p-values have now gotten unpopular, because they are very costly from a statistical power angle. So if you see here, and note that I do not stop it at maximum sample size, because Optimizely designed it in a way they do not have a sample size. They do not have a max sample size for always valid p-values. So that's why I also let it run further. So even with more sample size, it is quite costly on statistical power. So always valid p-values reduce your statistical power heavily. Now I have a question, two questions for you guys, in fact. Firstly, this is a question I meant to ask you earlier, but this is on errors of magnitude. Anyone wants to take a guess at why do early winners have exaggerated uplifts? I'll explain both the options that I've given. The first is that averages are not stable at low sample sizes. That is why early winners have exaggerated uplifts. And the second is that it is likely that high variance has led to an early winner. So what happens? So what this option is saying is that the high variance in the metric led to an early winner, whereas there was no true uplift. So why do you think early winners received from peaking will be having high variance? I here are yeah. Anyone else wants to take a guess before we move to the next question? Interesting, quite a skewed. So yes, both of the above is the right answer. Both the reasons, averages are not stable, they vary a lot, and that is why they sort of give high high uplifts. Finally, it is also likely that the metric has a very high variance. That is why the high variance itself has led to seeing a winner, whereas an actual uplift. So both are right answers. That is why we have exaggerated uplifts early in the test. Finally, now this is the question I want to ask, and this is a very crucial concept regarding statistical power. Uh, what does a low statistical power imply? Option one says that true winners will not be detected in the test, or true winners will take more visitors to be detected. I am asking this question specifically in the context of sequential testing. So, what does a low statistical power imply? This is very important to grasp. Interesting. Anyone else wants to? So there are two cases here, fixed horizon testing and sequential testing. I'm asking for sequential testing, what does low statistical power imply? Anyone else wants to? I'll give you a hint as well. There is one answer for fixed horizon testing, the other answer for sequential testing. You have to answer for sequential testing. What does low statistical power imply in sequential testing? Great. I think people have gotten it right. Now, this is a very, very important thing that I want to highlight. When we talk about fixed horizon testing, then low statistical power does imply an increase in false negatives. Like if you have low statistical power, then there might be some true differences that go unnoticed in the test. But when we are talking about sequential testing, then it is safe to assume that you'll run the test long enough for the winner to be detected. So if you are actually seeing a high probability to beat baseline, you'll let the test run long enough. So low statistical power always in sequential testing, it implies that you'll be requiring more visitors. So it is less likely that winners get and go undetected, but still low statistical power is costly because it will require much more visitors. So this is something that Optimizely did with their always valid p-values method. They said that they have 100% statistical power because do not have a maximum sample size. So because they do not have a maximum sample size, they would let the test run as long as possible and detect all the winners somewhere down the line. But The catch was that statistical power being compromised meant that visitors were required more than it would with other methods. So that is something to note. Okay, now I will move further. I want to highlight the pros and cons of the three ways, but I also want to say that I'm not, firstly, before delving into this, I'm not associated with any organization. I'm only associated with statistics as of now. If I have any affinity towards the solution by VW, it is because I developed it on my own. So, but I do not mean to highlight or reduce any company or any competitor for that matter. I only want to highlight what are the benefits and losses of the three methods. So wherever I see a benefit of some other method, I'll highlight that. Yeah, that's all. When I'm actually endorsing something, I'll let my audience always know. So now I want to highlight the trade-offs between the three methods. So with alpha spending, essentially, you get controlled false winners, as we saw. You get controlled false winners with all three methods. You have maintained statistical power with alpha spending and adjusted confidence interval, as we saw. Always valid p-values have a very low statistical power. Uh, Alpha spending and adjusted confidence interval method also allow for disable recommendations. Always valid p-values, at least in their vanilla form, which I have studied and implemented, they do not have a disable recommendation method. They only test for how wide the difference is. If it is wide enough, they declare a winner. They do not have a signal for disabling a variation. Finally, there is a predetermined maximum sample size, and for alpha spending and adjusted confidence, note that this is a pro and a con both. So without calculating a maximum sample size, alpha spending and adjusted confidence approach cannot work. And that is a con as well. It is a pro in the sense that you always know which maximum sample size you are going to hit. You have unlimited peakability with all three methods. So I have run extensive simulations with 100, 200, 300 peaks. And what I've seen is that the guarantees are ensured with as many peaks. It is not a problem. Although some methods do, so basically in the real world, some statisticians would recommend to have 10 to 12 to 15 peaks, not more than that. That's because sometimes the assumptions of statistical significance are not met in the real world. So it is better to be safer. So I'll also talk about it in the end. From an interpretability angle, always valid p-values are very hard. They're just a number that you cannot interpret in any other way. Alpha spending is good because it retains statistical significance as it is, but it changes the decision boundary. And for a lot of new experimenters who are not familiar with statistics, the changing decision boundary is a very alien concept. They do not wait for the decision boundary to be crossed. They only look at the number and take it as the exact probability that the chance that variation is winning. So that is why alpha spending, when we were developing a solution, we liked alpha spending, but we thought that we need to take it one more notch ahead because changing decision boundary is not intuitive to a lot of experimenters. I think adjusted confidence is the easiest to interpret because we designed it to be that way, that everything regarding sequential testing should be clubbed into one number. That will be your the statistical significance. Finally, the companies that I know there are other companies as well that are using these methods. But the ones that I know are alpha spending is used by Analytics Toolkit. And I think AB Smartly as well, because they are using the same stats engine. Then always valid p-values has been used by Optimizely, and adjusted confidence interval is a new approach that is now introduced in VW. So yes, moving ahead. Yes, so practical tips and tricks for sequential testing. This is the last part of our webinar. I'll be closing in 15 minutes. But yeah, let's move ahead. Firstly, there are some tips on when to select fixed horizon and when to select sequential testing. So I have 5 ideas that you can follow here. I will check quickly if there is any question that has been pending. Okay. I have 2 questions here by Nikhil. I'll take that up. I have 2, 3 questions here. Sorry. Just a second. Mean. Amish, please ask me this question in LinkedIn separately. I think I'm not able to get it. As mean and ST are high. Yeah, please, Amish, ask me this question separately. I'm not able to make sense of it right now. Is the VWO methodology open sourced? It is. We haven't applied to any patents or anything. It's a straightforward methodology. I think all such statistics research is open source. If VWO plans to publish a paper on it, I think it will be formally open source. Yes. Does the power, but there is no copywriting or anything there. Does the power analysis methodology differ for sequential testing? No. Power analysis methodology in the sense, what exactly do we mean by power analysis? So, okay, the sample size calculations. So it depends on the methodology. For instance, Nikhil, you cannot use the normal sample size calculator for always valid p-values because the method itself is different. For alpha spending and for adjusted confidence intervals, the normal sample size calculator and the power analysis works because those approaches are designed that ways. So yes. So now moving to the fixed horizon versus sequential testing. So I have 5 tips you can follow here. Firstly, what I want to highlight is that sequential testing is great. It ensures your statistical errors are within limits when it is correctly applied. But always everything about statistics runs on some assumptions, and some assumptions are sometimes not met in the real world. So fixed horizon testing is better because it is more robust to assumptions being broken. So suppose you have weekly cyclic patterns in your data, and the conversion rate, like one of the assumptions that all statistical significance frameworks make is that the conversion rate is the same across the population. It is homogeneous across the population. It does not change through different segments and through different time, which we know is not true. So fixed horizon tests are much more robust because they resolve a lot of assumption violations in the real world. So if visitors are not a problem for you, you can run fixed horizon tests. So like I know that very large companies who have a lot of visitors, much more than they can test with, they usually prefer to go with fixed horizon tests. It also generally is so if you are running with a very large velocity, so if you're running hundreds of experiments parallelly, it becomes physically very hard to monitor all those. And it is better that you run a test and forget about it and then just look at it after the required data has been collected. So prefer fixed horizon tests if you have so many visitors that visitors are not a problem for you. If it is a very crucial business decision, you are better off with a fixed horizon test, but you can take a balance on how quickly you want the result or how accurate you want the result to be. Fixed horizon tests can expected to be more robust. I won't say more accurate because theoretical guarantees are met for both, but because assumptions are violated often, fixed horizons are robust. If you have highly variable metrics, then sequential testing is likely to give an early winner only because of the high variance. Although all the methods that I've shared here, they do mitigate this problem to quite an extent, but still, if you have highly variable metrics, you should pick fixed horizon tests. For guardrail metrics, you should always use sequential tests. Why? So the idea behind guardrail metrics is that any crucial metrics if they are negatively impacted in a running test, the test should be automatically shut down. So if you are running them with fixed horizon, then guardrail metrics would not do their job. They would not shut down the test as early as possible. So for all guardrail metrics, you should always use sequential testing. If you have multiple variations that you are testing, then you should prefer running it with sequential testing with early disable. Why? Because you'll save a lot of visitors. So generally, when you are testing 3-4 different versions of an idea, uh, it is likely that 2 or 3 variations are actually bogus. So you can save a lot of visitors by disabling those variations early in the test. So if you have multiple variations, fixed horizon testing will linearly increase its visitor needs. So if you have 5 variations, it will require 5 times as many visitors. Sequential testing will require 5 times as many visitors in the start, but it will quickly start chopping down variations. So it will give you quite a big boost in the number of visitors that you have. So yes. Now checking if your engine is sequentially valid. Now, if you're using an A/B testing platform and you are concerned if it is sequentially valid or not, I think you can try out 3-4 methods to ensure that the engine is working fine. The first is if you have the luxury of having many visitors to test the engine out, what you can do is you run an AA test with 10 variations, same as the control. And then what you can judge is that how many variations actually cross the 80-20 mark. So like most of the variations will have a probability to beat baseline centered around 50% in an AA test. But the more extreme the probability to beat baseline goes on both sides, either towards winning or towards losing, the more the rarer that possibility is. So you can basically judge how many variations are crossing the 80-20 mark, how many variations have crossed the 90-10 mark, how many variations have crossed the 95-5 mark. So if you plot this sort of in a cohort sort of a way, you'll able to get an idea, a rough idea, if the engine is following the defined guarantees or not. So that is one way. I have a question here for people. In an A test with 20 variations, how many variations are likely to cross chance to beat baseline of 80%? So, yeah. In an A test with 20 variations, so you have 20 variations, how many variations are likely to cross chance to beat baseline of 80%? Anyone wants to take a guess? Anyone else wants to take a guess? I'll give you a hint. You calculate the false positive rate by subtracting the threshold by 100%. Guys, is it too hard? Interesting. Okay, in the interest of saving time, yes, the answer is right. The answer is 4. Why? Because you have a 20% false positive rate. 20% of 20 is 4. So if 4 variations are crossing 80, then you can roughly say that the engine is working fine. 2 variations out of these 4 should cross 90, and only 1 out of these 4 should cross 95, ideally. Another question here, and this is a very important idea that I want to share before we move forward. An AA test with 20 variations, we are giving a disable recommendation when the score goes below 10% and a deploy recommendation when the score goes above 90%. How many recommendations can you expect? Anyone else wants to take a guess before we move forward? Yes, 4 is the correct answer. The point that I want to highlight here is that if you are using two sides for disable and deploy, then you need to multiply the false positive rate on both sides. So this approach that I shared with you can be used on both sides. So if you invest those many visitors to run an A test with 10 variations, you get data from both sides and you can essentially plot it on a cohort and see how well it adheres to the line. If it is very, very off from what is expected, you can question if it is sequentially valid or not. So yes. Now the second method is to basically check is if the decision boundary keeps changing or updates when you peak or not. So that is one way you can check. I have a question for that as well. Changing decision boundary means which method has been used for sequential testing correction. Yes, you guys are right. Alpha spending is the method. Always valid p-values have a fixed decision boundaries. Adjusted confidence interval also has a fixed decision boundary. So yes, alpha spending is the method in which the decision boundary changes. Now another third method is what you can do is that any given point in time in the test, you can compare the significance that you are seeing with an external calculator. If it is sequentially corrected, the external calculator will never be sequentially corrected. It will always assume that you are collecting the entire data set and putting the data in. There is no reason for the external data calculator to be sequentially correct. So significance values should be conservative ideally. So one of the two things, two or three, not both need to be true. One of the two things need to be true. So if the third is true, which method is being used? If significance values are conservative compared to an external calculator, significance calculator, which method is being used? Okay. So in the interest of time, I'm moving ahead. Uh, Always valid p-values and adjusted confidence intervals both have the same effect. Even always valid p-values have the same effect. So it can be always valid p-values as well. Last slide, guys, before we close. Some tips to run sequential tests. I'll quickly go over these. And then if any of you has questions, I'll take them up. So I have some tips to run sequential tests. The first is that you should choose a minimum detectable effect on the lower side. So MD is used when you are deciding the sample size in advance. So you should not select the MD to be on the larger side with sequential testing. It should be on the lower side or whatever you would use with fixed horizon testing. Because if the uplift is larger than your MD, sequential testing will take care of it. It will give you a winner early if the actual uplift is larger than the MD. So don't worry about the MD with sequential tests. Just whatever uplifts you expect, take the lower end of it, set it as the MD. You should not generally disable test results without the engine declaring a sequentially valid recommendation. So a lot of people do this, that when uplifts are negative early in the test, they rush and they disable a variation. But this should not be done. If it is a sequentially valid engine, it should ideally take care of disabling recommendations as well. And you should check if it is giving if it gives disabling recommendations or not. If it does, then wait for the disabled recommendation before disabling variations, essentially. Do not increase the MD in a running test if observed uplift is larger. So some people might want to shorten the test duration by increasing the MD in a running test. This again has costs on false positive rates. So your false winners will increase. The fourth is in fixed horizon test, inconclusive results are considered as control is the winner, or you basically do not reject the null hypothesis. But in sequential tests, you should be very clear that inconclusive result means neither a winner nor a loser. Yes, with an inconclusive tests, you can choose to run them longer by putting in more data. If you are switching between the two modes, fixed horizon and sequential, in a running test, you can switch from fixed horizon to sequential, but not the other way around. Because fixed horizon demands that statistics should be calculated only once. You should not go from a sequential testing to a fixed horizon testing. Finally, even with sequential testing, because visitor behavior changes over the week, on some websites, there is a higher propensity to buy over weekends. So it is recommended that, especially in the first 2 weeks, you take a decision only in weekly cycles. So if you started the test on Wednesday, you take a decision on Wednesday only, at least in the first 2 weeks, so that whole 2 week cycles are taken in. Finally, as I told you, that if you are getting an early winner with sequential testing, give a rough 20-25% haircut to the uplift. The uplifts are usually smaller. So yes. Finally, yeah, any question, anything? We have reached the end of the presentation, guys.